When we talk about algebraic operations such as addition or multiplication, it's important to know which sets of objects they are applied to. For instance, multiplication could be defined for only the counting numbers, or for the real numbers, or for complex numbers, or for matrices with real or complex elements. And we could even define multiplication for more exotic objects. We can be quite formal and say that we consider the pair consisting of the set S and an operation, denoted by this asterisk symbol here. The operation is applied to two elements from the set, denoted here by F and G, to get the result. For instance, we might consider the set of all real numbers under the operation of scalar addition. We call the elements that are being combined the operands. That's -2 and 3 in this case. Let's now have a look at some of the terminology that's used in abstract algebra without going into too much detail. The first definition that we'll look at is closure. It's quite a simple concept, but it can seem quite difficult at first because of the terminology used. Closure basically means that when we combine elements from the set under the operation, then the result is another element from the set. More formally, a set S is said to be closed with respect to a given operation if by applying the operation to operands F and G, the result is also from the set. An example of a set which is not closed under scalar addition is the set consisting of the numbers 1, 2, and 3, because we can add two operands from this set to get a number which is not from the set. The next concept that we'll look at is associativity. An operation is said to be associative if the order of operations doesn't matter. More specifically, if we take three operands A, B, and C, then the product of AB with C is the same as the product of A with BC. An example is the set of real numbers under scalar addition. If we added together the numbers 2 and 3 and then added this result to 1, then we'd get the same result as if we added together the 1 and 2 and then added 3 to the result. It's important to note that associativity only guarantees that the order of operations can be changed, not the order of operands. For example, it doesn't guarantee that we can swap the A and B. Associativity is a tremendously useful property, but not all operations are associative. For example, the power operation on the set of real numbers is not associative, because if we group the operands like this, then the result is not the same as if we group them like this. Where associativity lets us change the order of operations, commutativity lets us change the order of operands. So, commutativity guarantees that for two elements A and B from the set, the result of applying the operation in this manner is the same as the result of applying the operation in this manner. An example of a commutative pair is scalar multiplication on the set of complex numbers. If we let this expression here denote the set of n by n matrices whose elements are real numbers, then this set is not commutative under multiplication. Students often confuse the terms associative and commutative, but these terms do convey a similar meaning to their use in everyday language. For example, in the expression A asterisk B, commutativity allows A and B to move around, to commute. In the expression here, associativity allows us to associate B with A, or to associate B with C. An identity element from a set under a given operation is an element with this property here, where E denotes the identity element. It's the element which maps every other operand to itself. For instance, if we're dealing with multiplication of real numbers or complex numbers, then the identity element is just the number 1, because we can multiply any element by 1 to get itself. In common with all the terms discussed here, when we're talking about the identity, we must be clear about what the set is that we're dealing with, and what the operation is. So we can talk, for example, about the additive identity or about the multiplicative identity. Have a think for a moment and try to decide what the additive identity for real numbers is. Hopefully you realise that it's just the number 0, because 0 can be added to any real number and any real number can be added to 0 without affecting the result. Defining an additive and a multiplicative identity for matrices is something that we'll look at in another part of the course. The last concept that we'll look at in this video is the inverse, and here we're talking about the inverse of an element, which is not quite the same thing as when we talk about the inverse of a function. If we take an element q from our set, and if we denote the inverse of q by writing it with a superscript -1, then the inverse has to satisfy this property here. In other words, if you combine the inverse and the original element under the operation, then we recover the identity element. An example is shown here for multiplication of real numbers. 1/3 and 3 are mutual inverses, because when we combine them we end up with the multiplicative identity. It may be the case that not all elements in the set have an inverse. For example, for multiplication, the number 0 does not have an inverse.